it's recording. Okay, good. So that in this one, do you guys still have any question on the principal component of factor analysis? Is something that you want to discuss before I move on to the repeated measures analysis? Principal component, how to do the homework, how to present that one, how to write the answers. So
I think I'm good on most of it. I needed some help on how to describe the variation explained by each of the factors. So that let's say that I'm looking
yeah,
at
that's why that again, that if I have that to scan a one shot, that fortunately or unfortunately it's not there, then I have to write it down. Okay, it takes a while.
no, I mean, I'm just because there's a table that comes out when you do the factor analysis. There's a table called eigenvalues of the correlation, right? And when you look at proportion, you see your decimals there, right?
Yeah. Okay.
Let's say one of my decimals is 0.39.
Okay.
And so I say 39% of the variance is explained by that first factor. Or do I say 0.391? Like, how do I?
So you're talking about how many decimal places to be kept over?
No, like the way I wrote my sentence is just, for example, factor 1 explains 0.3911 of the variance, whereas factor 2 explains 0.2497 of the variance. But I'm wondering,
variance of whose variance? You have to mention clearly whose variance been explained.
In the 14 variables that were chosen.
Okay, 14 variables that variance being explained by the principal component one. How much variance of all these variables can be explained by the principal component analysis?
Do I express it as a percent, or can I just leave it like that as a decimal? It's out of 1, obviously, but
no, you can leave it as a decimal or percentage or as a fraction. Doesn't matter. Either way is fine. Any way is fine. You can either keep it as a fraction. Like let's say that 3/4 of that variance of that all these variables being explained by principal component 1, and the rest will be that gonna be the distributed among the, let's say in the case of 2, let's say we have x and y for your convenience, and the x variables and y variable, they both will contribute to build up the principal component 1. Who's contributing? None other than the variance. Variance is the key part. The variance, then how much of variation of the x would contribute, how much of variation of this one is contribute is another discussion. But when it comes to the principal component explain the total variance of that one up to certain fraction of that one. You can say like that. Can you remember I said that? Okay, I'll very clearly, I can sometimes show to this screen too, the camera, and then sometimes show you. Give me 1 second. That way, okay. Okay, let's say that you have this picture. Look at this picture. Can you see? It's not clear, no? I don't think it's clear. It's not clear at all. Okay. Can you remember in the first example that I was going through, that in that way that I picked the 2 variables, x and y. Okay. Then right after that, we did the several things. We found the eigenvalues. Okay. And then we went to the eigenvectors. Then we went to the load-ins. Okay. You can use either load-ins or eigenvector for your principal component. Doesn't matter. It depends on that how you're going to scale it, and then what do you need at the end of the day. Okay. But in my case, that what I did was in the beginning, I used the loading. Sometime on the printout, you have eigenvector. Doesn't matter. There's no big difference between those two. Doesn't matter. How do you convert the eigenvector into loading? You have to multiply that vector by square root of eigenvalue. That's a different discussion. But once you get everything, you're gonna write. Can you remember on the printout you have a PC1, PC2, and column wise. Row wise you're gonna have what? X and Y, where 2 variables. Okay. Now you can add all these load-ins or eigenvector values squared and add. Sum of squared, let's say for in my convenience, I'm going to call them load-ins. Column wise, sum of squared load-ins. The other way, if you add the square, we're going to call the communalities. Can you remember? Two ways, but they both will explain the variance. Whose variance? One is principal component going to explain the variance of x and y as a proportion. The how much, say that like for instance, that let's say that principal component one, we can say like this: how much of variance of x and y, okay, that is whatever the variance you can see, okay, being explained by principal component one.
Can you see my annotation? Can you guys see my annotation?
Yeah, there you go. Yeah, I can see. Okay, you're right.
So you can do the same thing if you're able to write on the.
I can write on the book.
I wanted to ask, for example, yes, if I have.
Okay, I'm gonna write this page. Okay, then I can write this. I can write on the book for sure. Yeah. Okay. So this is okay. After all these things, okay, I'm gonna write here for you to see clearly. Okay. See, I have a principal component 1, principal component 2. I have an x here, I have a y here. Okay. I'm gonna say I have a root 3 over 2 over here, negative root 3 over 2 here, 1/2, 1/2, like that. Okay, let's say those are the numbers. Okay, those are the numbers. See, the loadings or eigenvectors, either way, doesn't matter. Okay, so you can get this done in two ways. So I'm gonna say when loadings are used for principal components, can I use the loadings? Yes, I can use the loadings. Okay, I can use the loadings, so I can use the eigenvectors. Either way, okay, either one. Okay, either one can be utilized. Okay, so this one, this one.
So the communalities, if we go across, that should be, if I have 14 variables, that should add to 14, right? So it tells me out of 14, how much of the variance is explained.
Yeah, exactly. That you can, when you learn for the 2, you can extend the same idea for 14. That's the best way to do that one. Okay.
Yeah, it's just
learn with the smaller one and then add the same, extend the same idea to the bigger one, bigger picture. But I'm trying to say that this one, when the eigen, instead of eigen values, I'm going to use the loadings. Okay. That's why I want to line up this one very clearly. Okay. There are two settings over here. Sometimes I use the loading, sometimes I use the eigenvectors. Okay. Loadings, okay, here. So then if you come in this one, see, if you do this one, see, that down the column in each one, sum of squared loadings, you can say these are sum of squared loadings, no? Sum of squared loadings. See? How do you get that on sum of squared loadings? See, root 3 over 2 squared plus root 3 over negative root 3 over 2 and 3 over 4. See, like that, 3 over 4 and 6 over 4. Then you have a 3 over 2, 1.5. This is nothing but what? Eigenvalue. It should come to eigenvalue if you use the loadings. The similar fashion, you can do the same thing here. So this one, how do you explain this one? That's the question now you have. So you can say that that's the variance. How much of variance? See, how much of variance? See, variance of, see, x and y, both, okay, together. That is var of x and y. See, var of x plus var of y. In this case, those are already we know. I'm going to say 1 plus 1, which is 2. Okay, being explained by PC1. It's not the proportion. I simply say that much will be explained by this one. Now you have to go further down and say, hey, I want to tell this one as like a proportion. Can I tell that one? Yes. If you do the same thing for this one, you can get over here 1/2 squared plus 1/2 squared So you're going to have a 1/4. 1/4 means 1/2. See, which is 0.5, no? That is lambda 2. In a similar fashion, you can say that's the how much of x and y being explained by PC2. Now you can tell the same thing as a fraction. Okay. Now I'm going to write as a proportion. Okay. Proportion of variances x and y being explained by PC1 is how much? Lambda 1 over lambda 1 plus lambda 2. See, now you can give us a proportion. So that means you have 1.5 for this one 1.5 plus 0.5. It's nothing but, see, this is going to be lambda 2, okay? Yeah, I'm talking about in the previous page, see, lambda 2, lambda 1, see, this is for PC1, for PC2. See? So this is going to be, see,
so you're going to say 75% of the
75%, exactly. Now you see
in the two variables is explained by principal component 1.
75% of that 75% of variances of x and y together being explained by that guy. It's a good thing. I mean, like that much of that variance being explained instead of going to x and y, the single element gonna explain that much of variance means you don't need the other PC2. Can you remember? It is gonna be consistent even with the what? Kaiser's rule. If you go ahead and check with the Kaiser's rule, anything more than 1 will be taken into account. I don't need the PC2, no? Look at, go to there. That's then, see, by looking at the lambdas, on the other hand, you can figure out, hey, I don't need the lambda. I'm going to keep the lambdas. Lambdas means the eigenvalues, the principal component whose eigenvalues are more than 1, which is PC1 is the only one in this case, the most suitable candidate. The other one is less than 0.1. And on the other hand, by looking at this 75%, you are more happy and say, hey, one component will explain 75% of the variation. That's more than enough to get our things done. That kind of a broader discussion, you can expand any way you want and nicely, and you can elaborate as much as you want, write like a whole day, and then make it like a novel or like a nice thing. You can add spices and everything and like that. But the bottom line, the core part here is how much variation of x and y will be absorbed into this PC1. It's the key part, the variation. Then the next one for sure, 25%. That 25%, do we have to add to this one? No. If you're going to add that one, you again work with the two variables. You don't have to in this case, no. But when it comes to 14, you can systematically reduce that one to like around 6, 5. Based on that different rules, you're going to come up with the different things.
And the sum of those communalities, the sum is going to be that same percentage, right? So let's say I have my 14 variables and I'm going to add those up, divide by 14, right? Let's say it's 12. That's exactly that same percentage.
That goes the other way around. Okay, I'll show you. Yeah, you know that one. Okay, as you said that sometimes those numbers going to be same as these numbers. Look at in this case. Communalities, I'm going to do it this way, see?
Yeah. So it's going to be like the
root 3 square.
Yeah, 0.8, yeah, radical 3 over 2.
It's going to be how much? It's going to be 0.5?
0.8, I think.
No.
Radical 3 over 2?
3 over 4, no? 3 over 4 plus 1/2.
Oh, yeah, you're squaring it, yeah.
I'm squaring 3 over 4 plus 1/4. Do you see that on 3? I'm sorry. Root 3, okay, I'm sorry. Root 3 over 2, this on 1/2, see? So it's going to be, I'm going to write this on one more time. 3 over 4, this on 1 over 4. Is that right? No, 3.
Yeah, 3/4 plus 1/4.
No.
I was asking about the communalities. Like,
yeah, that's the one that I'm okay. Root 3 plus 1/2. Okay, 3 over 4, 1/4. It's gonna be 1, no? It's 1. 1. This is 1. This is 1. See, that means that one, see, that one, then the other way around, then we can do this one too. This one, we pretty much get the same answer, no? Is that the same answer? Make sure I put
that. So yeah, it should equal 2 because there's 2 variables, right?
Yeah, 2 variables, same thing. See, 1 and 1. See, 1 and 1. See. So variable. So if you're gonna see, do the same thing here, you get the 1 here, 1, 1. See. So what are those then? See, can you remember? Coming on.
That's the total, right? 2, and then you're gonna say.
That's the total. Look at the x. Look at this one. This one is nothing but the variance of whose variance? In the beginning, that's the variance. Look at I utilize that one in particular case because when I started, their variances are 1 and 1 and covariance are negative 0.5. Okay, for this particular case. Okay, but that in example, when I was doing the exam, that in the class, I didn't divide by 2. It doesn't matter. You divide by 2. 2 means n minus 1. You have a 3 observation. So I divided by the degrees of freedom, which is 2. Then it came like a way that I see now. But when I was doing in the class, it's a little bit different, but it's the same thing. But I'm trying to say here, see, 1 and 1 is nothing but the variances of this guy. So how do you explain that one? That is nothing but how much of variance of x, variance of x being explained by PC1 and PC2 together. The x, not x and y, only x. You see, focus on x. How much of variance of x being explained by PC1 and PC together? Now you need a proportion. Proportion is what? Half and half. Is that right? 50-50. 50-50. Like that. You can 50% of the variation of x. See? No. This means that by this PC1 and PC together. See? Explain. See, when it comes to total variance, explain the half of that variance of that guy. See, 50%. See, as a fraction. See, this is the variation. But total variance between x and y, out of x and y, the both. Okay, x and y. Because we're gonna take into account these two together and these two together at the same time. See, when you go this way and this way, these two put together, you are adding these two together. Then you can say that that's how you get a fraction. See, here too, see, you get a fraction here, see. Lambda 1 plus 1, lambda I do what? See, proportion of variance of x and y being explained by PC1 and with respect to what? PC1 and PC2, okay? It has to be explained like that way, see? Proportion of, whose proportion? Why I'm talking about the proportion? Whose proportion? Then you're going to consider PC1 and PC2 together. Out of PC1 and PC, if you put together, PC1 explain how much of variation of x and y? 75%. How much variation of x and y being explained by PC2? 25%. Together, okay? The similar fashion here, you can say, see? Similar fashion, you can say, together, x and y, see? X and y, see? X and y. See? X and y if you take into account, but if you go this one, x, how much being that explained by the PC1 as a fraction, 1/2. How much of a variance of x and y being explained by PC1 and PC2? That's true because that its variance is over here, see? But in a certain way, some practitioners scale this one to get 1. Some people get a scale to this one to get the lambdas, okay? Especially when it comes to the square loadings, okay? So you can tell this one, how could you gonna say that this one? You say that how much of the proportion of variance, see? I'm gonna write here, okay? For the second one. Okay? Proportion, see? Variance, okay, of x being explained by PC1 and PC2, and together PC2, in this case, how much? See? 1 over 1 plus 1, which is 1/2, 50%. 50%. Okay. Same way, you can write the same thing for y as well. See, for the y2. Okay. In a similar fashion, you can write the same thing for y. Okay. See, here proportion of variance of x and y being explained by PC1. Here proportion of variation of x being explained by PC1 and PC2 together called the communality. Okay. On the other hand, if you do something, excuse me, if you do something over here, if you go ahead and check the principal component 1, where's the principal component 1? This is the principal component 1. Okay, I'm going to write the principal component 1. This is the principal component 1. Okay? This way. Okay. This one principal component 1. So component 2. Sorry. So if you write the principal component 1, which is, I can say, √3 over 2x plus minus √3 over 2y. Is that right? Yes. Then if I find the variance of this guy, variance of PC1 is, I'm going to utilize this formula, variance of ax plus by formula. The variance of a linear combination is given by a squared of x plus b squared variance of y plus 2 times AB covariance between x and y. From that original covariance variance matrix, you can get all these values. Our A is what? √3 over 2. Okay? √3 over 2. 2 squared. Variance of this one is 1. And again, √3 over 2, negative. See? Negative √3 over 2 plus 2 times √3 over 2 A. P negative √3 over 2 times covariance of this one is negative 0.5. So when you simplify this one, you get 3 over 4 plus 2 get cancelled off. 2 times 2, 4. Then 3 times 3 over 4, I think. 3 times 3, negative, positive. 2 get cancelled off. 2, yeah, 4. Then this gonna be 9 over 4, not equals to lambda 1, which is 1.5. See, not equals. But you can scale this one in such a way you can get this one equals to the other one as well. Okay, but here you don't get the lambda. Okay? Not a lambda, not equals to lambda 1, which is 1.1. You can, in a similar fashion, you can do the same thing for the other one too. See. But on the other hand, if you use the eigenvectors, the picture gonna change a little bit. Okay, this is using the loadings. See? This is using the loading. See, look at the when eigenvectors are used. Look at what's gonna happen. PC1, PC2. Here x, here y. I have 1 over √2 this time. Negative 1 over √2, 1 over √2, 1 over √2. Okay. Then you can easily calculate the sum of squared loadings. Sum of squared loadings, which is 1 over √2 square plus negative 1 over √2 square. So 1.5, which is 1. 1 not equals to lambda 1, which is 1.5. See? The same way over here, the same thing. See, 1 over √2, this one becomes 1 over √2 square plus 1 over √2 which is not equal to lambda 2, which is 0.5. Lambda 2 should be 0.5. On the other hand, I'm going to write the PC1, see, PC1, which is 1 over root 2 x plus minus 1 over root 2 y, and then find the variance of this guy, wow, PC1. I can remember 1 over 2 squared, y of x, which is 1, plus negative 1 over root 2, y of y is plus 1, and 2 times 1 over root 2 times negative 1 over root 2, covariance is negative 0.5. See? Negative 0.5. Then what do you get? You're gonna get here 1/2, 1/2, 1/2 plus 1/2, and then you get the negative, negative, positive, 2 get cancelled out, plus 0.5, which is 0.5, which is equals to lambda 1. See? Lambda 1. In the previous case, when you're looking for that variance of PC1, it did not produce that one because we were using the loadings. It depends on the loadings of the eigenvectors. Doesn't matter. Interchangeably, practitioners are using that one, but it has no any heavy weight on it. Okay, that's a rough idea what I'm trying to explain over here. Okay. So, any other questions? Anything that anybody has anything you wanna look at it before we move on to the repeated measures? And then based on what I have that this facility, just try to do as much as we can. Okay. Anything. Okay. But you know that the repeated measures, in order to, before this one, that repeated measures, I think you have already seen this one, because you have already utilized that completely randomized designs, the design of experiment in which that we were talking about the comparing and contrasting more than two populations, and their means will be compared and contrasted. Can you remember? Analysis of variance. We were using the analysis of variance in order to compare and contrast. Okay, so and what we're gonna do over here, measures. Okay, so we have, when we do any kind of like a, what are the things, the basic, see, we can say basic. Okay, there are two the basic objectives. Experimental design. What do you mean by experimental design? There are two types of statistical settings. One is experimental, the other one is observational. In experimental one, you can adjust design the experiment. Let's say that if you really want to know that how that the smoking can affect the lung capacity in men or women in the USA or across the globe, you can simply carry out a certain experiment in which you observe the lung capacity after a certain period of time. Let them to that these people to be involved in this experiment with their own consent, and then giving some perks and everything. And once they involve with that one, that who has already satisfied that all the requirements, criteria, and the legal aspect of that one, once they get into this experiment, and once they are involved with that one, they've been given that to smokers certain pack of cigarettes, or the certain number of packs of cigarette per given day for a certain period of time, and then after certain period of time, they can observe that. Or they can design that one. At a certain age, they start, and at another stage, a certain age, they're going to stop it. And within this, during this particular period of time, they can just simply ask them to that smoke, and then after that one, then they can how could you gonna design in the very beginning? In order to design that one, you have to have a two groups. One group is called the you see. Sure. Yeah. Okay. So then in that particular that experimental design, what are you gonna do? You're gonna design that one having a two groups. One group is called the treatment group. The other one called the placebo, the control group. This one treatment group is the one that people who are involved with that one. Sometimes they know predetermine that these people gonna go to this treatment group. We predetermine that these kind of a people gonna go to this control group, like that. We decide that now, predetermine, or we randomly assign. We randomly assign. We randomly assign. We randomly assign that different people for different groups. There are two groups, control and the treatment groups, that whoever come randomly being assigned that without taking into account anything, we randomly we do this. And that's a completely randomized design. But in that case, that you have a two groups, one group not gonna get, they're not gonna smoke, the other one they're gonna take the placebo. Placebo means that which does not contain so that some kind of that artificial, that chemical, artificial something that it doesn't have that real tobacco. So after a certain period of time, let's say that they're going to carry out this one 10 years, and then they can check the lung capacity. In such a case that those are that particular case, you can say that experimental design, because that you have already experimented. Some case that you have a observation. But in here that I'm talking about the experimental design, in which that we're going to design that one in such a way that the output will be that measured after a certain period of time, or being repeated for a long period of time, or that we can sometimes that same thing being check from time to time, and then with the some kind of that the sensor data, that some people they're going to involve with that one, they might going to drop out from this particular experiment. In that way, we're going to have some sensor data. Once the sensor data get into the picture, that all the experimental results going to be messed up. In that way, that we have to use different kind of techniques. But anyhow, here that we mainly trying to assign that our treatment, or that our subjects means the people who are receiving that treatment are called the subjects in this experiment. They're gonna be given that treatment in a certain way. In that way, that sometimes that not only one person might not gonna that receive that only that treatment, they might gonna get the placebo as well. That's kind of a discussion we are trying to build up in repeated measures. The same person gonna experience not only that treatment and the other all the treatment. Let's say that you want to introduce a certain check at which drug would be the best drug out of 4 types of drugs. Then if you get the subjects, you're not gonna let any person being randomly assigned for one drug only. Instead of doing that one, what we're gonna do, we trying to get the person and then have that particular person to that experience of all the 4 drugs, kind of like that kind of a process called blocking. We're gonna block that one. Block is done to its extreme in that repeated measures. In repeated measures, we're gonna do that one in extreme. That's what the repeated measure is. Another kind of like a blocking design under that, rather than having the completely randomized design. In the completely randomized design, treatments, that particular person not gonna receive all the treatments, just one treatment only, either placebo, that one, or either one drug A, B, C, or D only. But in this case, once they've been blocked, why we are blocking that one? In order to minimize the variation. Variation among the what? Variation that is due to what? That the data has a variation due to that variation of that some characteristics of the individual who are involved with that one. That has to be minimized. One procedure is called the ANCOVA, analysis of covariance. That procedure has all, I think you might or may not have learned it, but anyhow, that's another way of that suppressing that that unnecessary that error, the reducing the error variance or the error or the variation among those subject using the analysis of covariance called ANCOVA. In addition to that, here we are learning about the repeated measure in order to reduce the error variance by blocking. And by blocking means like supplying the treatment for the same person, let the same person to experience all the treatments in this case. In that way, we can even reduce the number of individuals being involved, not like in a completely randomized design. In another way, I can show you that how these completely randomized design one of work that one, okay, with another example later on. First, I'm going to complete this one, what I'm writing right now, okay? So in this design of experiment, there are basic two objectives. You have to eliminate, see, elimination of systematic bias. You have to eliminate bias. And then second one, reduction of, see, reduction of error. Error within what? Within group, within the group. See, group, or we call that one cell. Within, see, group. See. So this one, we can say the main reason, see, the main reason for within group, see, okay. Great, thank you. Within, okay, I already started, okay, repeated measures, okay, within group, okay, within group, inside the group, not between the group, inside the group, whatever the group they've been assigned to, like a control group or the placebo group, okay, within the group, okay, variability is, see, that variation of your reading or data is individual differences, see, individual differences or characteristics among these subjects, among the subjects. Subjects means the participants, okay? Okay, that one. So once you have that one, that, yes, how you're gonna get the within the error. Error is due to the fact that the individual differences among the subjects. If there are no any differences among the subjects, then there's no error within error, within group error, okay, within group error. See, within group error, they're not gonna be something like that. But due to the fact that there's that difference among the subjects, we're gonna have some kind of a variability within the group readings or in their data. So the one way of reducing, see, one way of reducing variance or that error is through what? Through ANCOVA. ANCOVA means analysis of covariance. Covariance, not the variance, analysis of covariance. That's one procedure. That procedure we don't gonna discuss. Instead of that one, we're gonna go to second one. See, another way of reducing, see, error or variability among subjects through what? Blocking on a variable. See, block, we're going to do the variable. See? So the second method, blocking. We can say randomized block design, RDB, instead of using the CRD, completely randomized design. There are there are different types of design when it comes to the experimental design. As I said in the beginning, there are mainly two types of studies. Studies are done in observational studies or experimental study. In observational study, you just simply observe and then record all the data. In experimental one, you just design the experiment and then take the data after a certain period of time, taking into account all the factors about that during that time period. Sometime you're going to carry out a certain experiment within a given time, then we're going to call the type 1, and within like until that certain number of subjects, so components. Okay, I am applying this one even for the electrical, electronic, mechanical or chemical component as well, not only to the human subjects. For anything, when until that certain number of failures have occurred, there are two ways. If within a given period of time, let's say 2 years, type 1 experiment, type 2 experiment, that in which that we're going to wait until a certain number of failures can occur. So there are different ways that we can design this experiment. During that particular period of time, some participant, they're going to just relocate. Some participant, they're going to experience the event. Event can be sometime the death or something, that we're going to define that one based on that scenario. So they are missing, we're not going to miss in that data. Some people, they're going to just leave our survey, or that they're not going to participate any longer. They say, I don't want to be a part of this one. And then their whereabouts are unknown. In that way, we don't know that after that they left that experiment, how long they're going to survive. That means that we are having missing data. So censored data, then we have to deal with the censored data. But anyhow, we don't go to that far. We're going to narrow down our discussion, restrict our discussion very nicely to like a very tight domain called just a complete data. Because when you expand to like the censored data, there are several types of censored data, type 1, type 2, truncated, so many things. Okay. Anyhow, when we come to this one, in repeated measures, see, design blocking, see, blocking is carried out, see, carried to its extreme. What that means, that is, we are blocking on each subject, see, rather than the variable. Each subject, see, each subject, see, each subject. Thus, see, variability among the subject due to individual differences is completely removed from the error term. No variation. That's the reason we are doing repeated measured. It's a kind of like a blocking design, but the blocking has been done to its extreme. See, and push to the corner, and then we're gonna do like that. So mainly in the design of experiment, main designs, you can see, design of experiment, see, experiment, see, DOE, we have mainly what? Completely, see, completely randomized design. CRD. The other one, randomized block design. RBD. Randomized block design. See, you might have seen these stuff. So in repeated measures, we're gonna do the randomized block design to its extreme. Okay, in a large scale. See, so let's say that for another example, I have that See, I'm gonna have several golf ball brands. See, A brand, B brand, C brand, D brand. See, these are the golf ball brands. How could we gonna figure out which brands will be the best brand that we have to utilize? You have to design an experiment. How could you gonna design the experiment? Either using blocking or completely randomized design, CRD or RDB. CRD or BRDBD, the one that we have to figure out. Can we get this done in both ways? Yes, we can get this one both ways. What are the advantages of using one over the other one? Like that kind of a broader discussion we built up. But mainly in repeated measures, see, we are here. See, this is nothing but the repeated measures, randomized block design. See, this one design of experiment DOE. See, so like that one, let's say that if you really want to use in that CR, the completely randomized design, what are you gonna do? You get 4 brands, large pool of that from a large pool of golf balls from that brand A. You're gonna pick a sample. Let's say I'm gonna pick 10 balls. I'm gonna pick 10 balls. See, if I pick the 10 balls, what's gonna happen? See, they are readings, and then I'm gonna see that the golf ball will be struck with that this. Let's say 10. See, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10. See, that's for the brand A. See, we need a dagger that see, what do you need in order to get this done? Let's say that 10 balls from the brand A being selected, and then again, okay, then this is a golf ball. See, golf ball. And brand B, we have those readings too. What are these readings? Readings when the balls are being struck by this golf club, how far it's gonna travel. That's the distance. Those are the distances. Okay, see D, we do the same thing. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like that. Okay, readings. What are the readings? These are the distances. Okay, that's the distance. You can say the distance. The readings would be distance. Your y is distance. Okay, y is the distance. Distance, y distances travel when or struck by golfer, human golfer or robotic golfer. Let's say human golfer. See, human golfer using a certain golf club. Okay, you're not going to change the golf club using the same golf club, and the people, even the golfers, you can pick from that one. For see, from a big pool of golfers, you're going to pick 10 people and ask the 10 people to hit on that one. Instead of that one, you can use the same person to hit on this 10 balls, because we are not interested in picking who is the best human golfer. Rather than that one, we can use the same golfer, but we're going to change the balls. 10 balls. See, these are 10 balls. See, I'm going to say 10 balls. See, 10 balls from brand A. 10 balls. See, 10 balls. 10 balls. See, 10 balls. See, look at. Or each ball being struck by how many people? See, 10 ball, 10 golfers. See, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, then all 40. 40 golfers. 40 golfers, 40 balls. See, like that. But there is some issue coming over here, because that when it comes to that golfers, that the skills gonna affect to that one. See, this is not the same person not gonna hit on the par B or C or D. They just focus on this one only one ball being hit by this one. See, and on the other hand, let's say one person being utilized to and ask him to that hit on the all the balls, 10 balls from the brand A, and then he's done his job, he go away. We pick another person, he's gonna hit on this one. See, all these. See, and get another person. See, another person. That would not create a big variation, because that variation should be taken into account. Because of that reason, you can each ball being taken care by the each golfer. See, you can say the 10 golfers for this one, another 10, another 10, another 10, all of it 40. See, 40 balls, 40 golfers. And the golf clubs, if you want, you can change that one too, but we don't have to take into account all the factors at the same time, because we can simply say that you are using that 40 golfers, 40 balls. Instead of that one, then a CRD, this one, I'm gonna ask one person to come, and then this person, then here, this person, see, this golfer, see, this golfer, see, he's gonna just hit on that, see, hit on only A only. Instead of that one, I'm gonna block this one, RBD. RBD means I'm gonna block and say one person to come and hit on all these, and they were randomly assigned to them. Okay, I get a one ball from, let's say the first one, he's gonna hit on D ball, B1, C1, and A, like that. So this first golf, second golf, see, he might gonna go AC, BB, like that, and keep going. See, and the last one, the 10th golf, gonna, let's say simply ABCD. Okay, so they got a chance to hit on that. Only, see, what is the advantage? We can use like a few number of golfers, that in that way that they get a chance to that strike on that golf ball for all the brands. Same person being utilized to get this done. In that way, here we have 10 golfers. 10 golfers. Here you can use the 40 golfers. Okay. It's been blocked. Same person gonna experience the treatment 1, treatment 2. We can call these are treatments. See, these are treatment. Treatment 1, treatment 2, treatment 3, treatment 4. All treatment. Here what? This person gonna just experience only one treatment. See? That's the way how we can reduce, as I said over here. See that in the other page. See that the repeated measure design blocking is carried to its extreme. That is, we are blocking on each subject. Thus, variability among the subject due to individual differences. Variability due to the individual differences. In the golf ball, the major one is nothing but the skills. The skills play in a heavy role, and the strength, skills and the strength has to be suppressed. That's what we are doing here. Skills and this one suppressed. In that way, there are no differences among these individuals. That error due to that fact will be reduced. Due to what fact? The differences. What are the differences in what? In skills, in strength, will be, see, blocked. See, that's what it says. The variability among the subjects. Subjects means like the golfers. Variability based on what's variability? Variability due to the strength and the skills. See, will be completely removed from the error term. So that vary will be completely removed if you're gonna design your experiment. On the other hand, you can even utilize only few golfers to get this done. So that's the major reason we are doing this one, to suppress the differences among the individuals within that given group. Look at here. We get another golfer, this golfer to that golfer, another golfer, another golfer, another golfer. Even within this group, your readings are, see, there's a huge variability, because that not all the golfers gonna have the same skills or the same strength. On the other hand, To remedy this one, you might be thinking, why we gonna use the human golfer? We can use a robotic golfer and get this done, this experiment. See, yes, we can get this done, but that we have to, sometimes we have to keep certain, up to certain point, that variability as well. We're not gonna take out completely the variability. Variability is playing a heavy role to make the real results perfect at the end of the day. So you're not completely taking out, but see, instead of that one, if you use the robotic cursor, you feel like, okay, sometimes that based on that, how that sometimes it might not gonna, even that there might be a variability, even the same person, the reader is gonna see. But here we are assuming that you are using the different individuals from this one to this one. They will have a differences are due to their skills in this particular experiment and strength. Okay, that has to be reduced by ask the same person to hit on this one. That variability can be tackled or taken care of, and then in that way we can easily reduce the error. That's the block design. This is what we are trying to do. This is nothing but the repeated machine is repeatedly getting into this one, and then do this kind of sorry, that same person will strike that on the balls from different brands, and at the end of the day you're going to compare and contrast, and then you can run that see, you can run here that if you want to, here you can calculate that x bar. See, let's say the difference is y bar of A, y bar of B, y bar of C, y bar of D. See, can you remember? I'm talking about that design, CRD design. See, then what would be your that the H naught? Can you remember? Analysis of variance, you're gonna say mu A equals to mu B equals to mu C equals to mu D. See, you're gonna say that pretty much all, you're gonna hypothesize that all these brands will produce the same average. On average, that they both, every brand's ball will travel the same distance on average, versus its counterpart. See, counterpart null hypothesis, at least, see, at least one of them, see, two of them not going to equals to each other. See, mu I not equals to mu j, sorry, mu j. See, mu j, I and j, I equals to j. See, here I not equal to j in this case, but here I and j can be either A or B or C or D. At least one of them, two of them not going to be the same. We don't know which two. We don't know which two, but that's why we have to go to the pairwise comparison. In addition to this one, later on you jump into the pairwise, two at a time, and then go narrow down two, and then two brands, two at a time, two at a time, two at a time. Excuse me. Then if you're going to do two at a time, how many combinations we have? See, you have a four choose C. Can you remember number of combinations? You can get into number of combinations. 4 choose 2. See, you have a 4 brand. See, 4 choose. 4 choose 2. 4 choose not C. 4 choose 2. 4 see C combination. See, some people they write this way: 4 comma 2. It's nothing but what? 4 factorial over 2 factorial times 4 minus 2 factorial, or that you can simply say 4 times 3 over 2 times 1. You can expand the 2. You're going to write that they are factorial, and then this is 2 and 2, 6. There are 6 combinations, 6 pairwise comparison, 6. Okay, sorry, here 6. 6 pairwise comparison. 4 choose 2, 4C2. C stand for the combination. You know this one. You have learned already these things, I think, in previous classes. Combinations. See, when that order doesn't matter, you go to combination. When order matters, you go to permutations like that. See, So 4 choose 2 from 4. You're gonna do 2 at a time. 6 combination A B A C A B B C B D like that. But anyhow, that's the kind of like that idea that why we are trying to do the repeated measures. In the repeated measures, we're gonna broaden discussion in other thing. If you go further down, okay. Then, measure is okay. From the error term in repeated measures, we talk about that one. We little bit mention about that one. Let's keep going down, and we were talking about one example. Example means like a not a that it's some data. See, this makes this means this makes this means I'm referring to that repeated measures. Okay, repeated measures design. Okay, repeated measures design. Oh no, no, not this one. Okay. This makes sorry, this becomes much more powerful. See, design, powerful design. Okay, or this block design. Okay, see PRD. Sorry, randomized block design RBD. Okay, design. Then CRD. See, they are different subjects are randomly. See, randomly. Okay, randomly assigned to the different treatment. Treatments means in that example, you can say the brand. Example, you can say the brands. Brands A, B, C, and D. That example. Different subjects means golfers. Example, golfers. Different golfers will be assigned. And different balls. Golfers and balls, both. See? Experimental. See? The golfer, see? In a CRD, different subjects are randomly assigned to different people. Then when it comes to this design, you're not going to pre-design anything, predetermine and say this person has to go this one. Most of the cases, whoever come to that one is from a large pool of that golfers. You're going to pick the people and assign to say, hey, you go to A, B, C, D, like that, randomly assigned. And you're going to do the same thing with the balls. But the block design, not like that. You pick the person, randomly pick, that's okay. But he has a chance to that experience all the treatments. These are the treatment. Then in order to, this is the analysis of variance. This part you have already done in the previous classes, how to get this done and see that which ball will produce the best results at the end of the day. Okay. But anyhow, that the CRD, the RBD become a very powerful tool. See, you go to this one. See, so therefore repeated measures design. Repeated measure design. I can call that an RMD. Measures design are measured under various treatments. Various treatments, conditions. Or treatments or at different points in time. You can do something today and then get it done in 2 weeks, 3 weeks, 4 weeks, 5 weeks, like that. Or you can do the way that we did under this different condition, brand A, brand B, brand C, brand D. Okay. So under this discussion, to make you that whole discussion very easy, I have categorized this into several groups. Okay. The first group, we're going to call the single group, the first single group repeated measures. See? Measures. Design. Okay, next time I'm gonna write repeated measures define. Only single group. What that means? This one you can say example, same example that we had earlier. Study the effect of. See? Study the effect of, like the 4 brands or that I was talking about in previous example. I can talk about something like a 4 drugs. 4 drugs. 1, 2, 3, and 4. See? 4 drugs. You're going to study the effect of 4 drugs under this categorization in repeated measures, RMD, under this or the blocking design. Under that one, how that can be, you saw that earlier, we did that one, but so you can get a rough idea. And then I'm gonna make it more formal, this one. It's the same thing that you saw in the ABCD in that golf ball experiment. See? Okay, then we can check about the drug, which is the treatment. In the golf ball experiment, treatment is what? Nothing but the brand. Okay. And you can call this one 1, this 2, this 3, this is 4. See? These are subjects on this side. Okay. Subjects. You have a 1 first subject, second subject, third, fourth, fifth. Okay, can you remember in golf ball example we had 10. What are you going to measure this one? What's the y variable? Then you have to think about what would be your y. Y also. See, what is y? In that particular example, you measure the distances traveled by the ball when they were struck by a human golfer with using golf club. See, can you remember? The distance traveled when golf ball is struck by a human golfer using a golf club. Okay. Even a golf club, there are the very different types of that clubs, but you can change that one. But for time being, we just not gonna change that one. In that way, we can take into account that factor too. But here, in this example, that under this one, you have a drug would be your treatment 1, 2, 3, 4 subjects are there are 5 subjects. What are you gonna? What would be your y? Y would be the response or reaction time. Response or reaction time. After that, these being given, drugs being given, how they're gonna react, that time being measured as a response as a y variable. That's the y variable gonna go to this one. If you get any reading, then those readings you can say this is your y1. See, you used to call that one y a b c d. This is y2. This is y3. This is y4. See, same person will experience all the 4 drugs. In a completely randomized design, it's not the case. 1 person per treatment. Per treatment per person. Here not like that. 4 treatment per person. See, they have a see. This person has a like a see. Gonna go through in that way. That would make a like a that any differences among these people due to the error variability due to that differences among these people, how they're gonna react to this particular drug can be minimized. The variability can be minimized at the end of the day or taken out completely, because in repeated measures, the blocking has been done to its extreme. See? this is very easy, that if you have that kind of a, like a, let's say that data set, you're going to have a data set. Let's say that I'm going to write that SAS data code over here, syntax little bit. See, data. See, I'm going to call that one way. See, one way. Okay, data. Then you can put the input, or you can recall your data set input. You can put y1, y2, y3, y4. See, then the lines. See, then the lines. So let's say that you have a first person, the second reading, third reading, fourth reading. See, 1, 2, 3, 4. 1, 2, 3, 4. One person, second, third, fourth. 1, 2, 3, 4, 5. See, then what is the procedure you're going to use? Okay, I'm sorry. GLM, general linear model. GLM stand for general linear model. GLM, general, or some people call generalized linear model. See? Then you give the model. The model, what do you have? You have a y1, y2, y3, y4. Because see, I'm gonna say something here. No univariate. I'll tell you why that means. No univariate, no uni. Because this experiment can be get it done. I'll show you. It is done in several ways. We're gonna broaden that discussion in that direction pretty soon. Okay, that one get it done. Using, there are two types of repeated measures: univariate repeated measures, multivariate repeated measures, or the complete CRD. Under CRD, can we get it done? Yes. Assuming that this is like a CRD one, can we get it done? Yes. Can we get it done? This one thinking that this is like a univariate case? Yes. Multivariate case? Yeah. In 3 ways we can get it done. And their results will be displayed when you run this one on your SAS output. You can see that one pretty soon. Excuse me, any example, but that's not enough. We have to know everything behind that one to that elaborately explain that one to the audience at the end of the day. See? No uni. They say I don't need the univariate analysis. Show me the multivariate and repeated multivariate repeated measure, and if you want, they can show that even CRD, completely randomized design, and then plus that. You go further down, you can have. Then you can say repeated. Who will be repeated? Drug. Okay. Drug will be repeated. How many drug? How many treatment? 4. And not only that, I need the contrast. I need the contrast. Contrast means like what? Comparison. The pairwise comparison with respect to 1. If you put 1, that with respect to 1. And then you can give the summary and means. Those things we can get it to. Okay. Contrast means see, contrast here means this word. Contrast. See, for pairwise comparison. 2 at a time. Pairwise means 2 at a time. Comparison. Pairwise comparison. So if you put the contrast 1, so pairwise comparison between, see, 1 and 2, 1 and 3, 1 and 4. 1 and 2, 1 and 3, and 1 and 4. So if you need the rest, you need the 2 and 1. If you put the 2 and 1 already done here. See, if you put 2 here, 2 already done. See, therefore 1 and 2 or 2 and 1, it means it's the same thing being repeated. See, so you're not gonna, the order doesn't matter. Order doesn't matter. That's why we say the combination. If order matters, we're gonna keep that one. Permutation is, those are permutation. In a combination, we had only 6 pairs. Can you remember? In the 4 choose 2 case, we saw that we got only 6 combinations. See, 1 and 2, 1 and 3, 1 and 4. The next one, not 2 and 1, drop 2 and 3, and 2 and 4. In order to do that one, we put 2 here. And the next one, 3 and 1, 3 and 2, already done, 3 and 4. See, like that. 1, 2, 3, 4, 5, and 6, the last one. Okay. So like that. See, if you contrast those things. Yeah, wise comparison between 1 and 2 and 1, 2 and 3. And 2 and 4. Contrast 3, 4. Pairwise comparison between 3 and 4. Then altogether you have what? 6, 3, 4, 5, 6. 2 and 3, 2 and 4, 3 and 4, 1 and 2, so 1 and 3, 1 and 4. That's what they were doing over there. But in such a case, if you see that, if you go ahead and let me see this one. Oops. Oh, no. It says so that certain. See, let's go to this example. See, this one has that data being given. See, for this one. See, syntax for single group repeated mention. Single group. Why are we gonna call the single group? This is the group. See, this group single. See, single group. See, single group. Can we get it done using the one-way ANOVA? Yes, that's the discussion we built up later on. See, completely randomized design means that one. Okay. So then they say that we have everything with the data already provided. See, 30, 28, 16, 34. Second or something like the first person, second person, third person, fourth person, fifth person. First person was experiencing the drug A treatment, drug B treatment, drug C treatment, drug 1, drug 2, drug 3, drug 4 treatments for each and individual. GLM procedure, no univariate, some remain. Yeah, it's not hard. Okay. all of that informations are already shown over here. See, contrast, variable, drug force. See, with respect here, they repeated measures, analysis of variance, of contrast variable, drug in represent the contrast between the nth level of drug and the first one. Nth level, in this means nth level. You see, so see, drug in stand for number, which one? Second one, third one, fourth one. 1 versus 2, 1 versus 3, 1 versus 4. So they are mean and errors and the degrees of freedom, type 1 sum of square, mean squared, F value, see, you can see that how could you going to carry out that comparison between two at a time. See, the mean and standard deviations over here. This is the key part. See, they're going to show you so many that parameters. See, Wilks lambda, different statistics, Eli trace, Hartley-Lowry trace, Roy's greatest root. We're going to talk about these. See, these different statistics. From time to time, different people have introduced different statistics to come up with the best result, because in the very beginning they start with something with so many flaws, so many defects, but later on, that's what that experiments are all the time do with the research. They try to remedy if they see any flaws or any drawbacks in their theory already being put forward into that statistical or data analytics arena. They have to fix it and then come up with the best one. They try to get the best one, but they keep going. There's no such thing called the best one. Best one is very relative. Relative means as of now. It might gonna change tomorrow, like that. Someone else gonna come up with a different idea. Okay. See. So this one, see. So you have seen these parameters. We have to little bit discuss about that one to one. So these are multivariate. See, multivariate one, univariate one not being displayed. See, multivariate one not being displayed. This one, see, repeated measure. Univariate test of the hypothesis within the subjective phase. This one. In addition to this one, see, these two epsilons are very important, because these are some kind of assumptions. We have those assumptions when our all the levels, these levels have their assumptions, then the assumptions are violated. How far this violation is measured by these epsilons? How far? See? So we have to talk about that one too a little bit. Okay. So that means this one. See? These all should have come from some kind of a distribution. See, not in this one. This one is this is a sample distribution. See, because it's based on the sample. There are 3 types of distribution we learned in the previous classes from the very beginning, and are 600 all the way up to here. Sample distribution, sampling distribution, and population distribution. And sampling distribution means the link between the sample and the population distribution staying in the middle. But anyhow, when the sample is taken, here we call the observed samples. These are observed based on the sample, but its counterpart, population, is already there. You built up the theory on the population. Okay. So you built up the theory over there based on this one. It's its population version. So the population version for a given level, for a given this Y1, for the Y1 readings not only 5. We believe that it's infinitely many data readings or the scores. See? Infinitely. If you have infinitely of them for the given this one, those can be easily fitted into a histogram. That histogram is nothing but the distribution. That distribution, they believe, neither that symmetric, sorry, that it's definitely a symmetric distribution, which is a normal distribution for our mathematical and this calculation purposes. The easiness of that, we're gonna consider that one as like a what? normal distribution. See, normal distribution. Those are normal distribution. But here, instead of going one at a time, you can take into account all these at the same time, called the multivariate normal distribution. Okay, multivariate distribution. Or you can consider these separately. In univariate discussion, you can consider this one univariate. If it is considered to be a CRD, completely randomized design, I'm going to consider this one separately. If it is a univariate repeated measures, I'm going to consider this one separately, this blocks. But when it comes to the multivariate, I'm going to consider this whole thing at the same time. In the multivariate case, if you want to looking at the assumption, this all will be coming from a multivariate normal distribution. That's our assumption. In addition to that one, sometimes these should have the same variances. When those variances are not the same from population to population, that has to be addressed. That has to be addressed. That has to be addressed by this epsilon. Okay. We're going to talk about this in broad range, okay? And very elaborately, we talk about this one. But it's not hard. You don't have to worry about the formula, anything. But I'm going to show you the formula on my side. They were already there. You don't have to calculate by some cases. But I think that for this particular one, I assign homework from the textbook. Some questions, 5 questions, okay? So some few things that if you know there's any formula for that, this one, see. Greenhouse gas epsilon like that. See, then that can be calculated when you see the formula. Okay, but here, you don't have to. Basically, you don't have to utilize that heavy formula to get it this time. Because sometimes the formula, and in some cases, formula being even given in that textbook, you have to just plug in something. That's very easy. Okay. But we're going to come to that one. But in order that continue this discussion, what I'm going to do, I go back to where I was earlier. This is a first, okay, little bit give a, this will formally complete this one. See, I'm going to say the first, the category, single group one. There's another one. You can get it done. This one, the same one in the second one. Okay. One-way repeated measures. Okay, one way. This is one way. One-way repeated measures. Second one, repeated measures. Where time. Time is the within subject, okay? Within subject, okay? Within the subject. Variable. Within subject variable. Okay. Let's say for this one, let's look at an example. This same thing, see. Now we're gonna see at a certain experiment that you have to after certain experiment, you're gonna take into account variable as a what? Within subject variable, see. Within subject variable, within the variable, we're gonna get the time now. First day, second day, after 2 days, after 3 days, after 4 days, after 5 days, certain experiment. I'm going to call this on Y1. This readings Y2. This readings Y3. These are Y4 and Y5. What is your Y? What would be your Y? Okay, these are the subjects again. And Y would be what? Verbal recall. Verbal recall. And you're going to read some kind of a word through them, and then is there any way that you can, how much of them you can remember like that, if you after 1 day, 2 days, 3 days, 4 days, 5 days, like that kind of experiment. Okay, verbal recall. See? Here then, see, 1 2, you're going to utilize 5 people. See, each person, within that person, the variable would be not like different drugs. This time the time, it has been measured over time, see, measured over time. See, measured over time. See, if you do this one, you can, how could you gonna do something like that? You see, I'm gonna call the data, I'm gonna call that one trend, okay? And input, what are the inputs? Y1, Y2, Y3, Y4, and Y5. And lines, see, 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And fifth person. See, and the model, see, and the model would be what? The model would be Y1, Y2, Y3, Y4, Y5. Again, equals to, it should be equals, there's nothing to be equal to. See, I'm going to say no univariate. No univariate analysis. And the repeated. This has been under the repeated measures. Repeated, but days, see, days, that's my variable. How many variables? How many levels? How many levels is here? So those are the levels. These are 5 means number of levels, okay? Number of levels. I have 1, 2, 3, 4, 5. 1, sorry. 1, 2, 3, 4, 5. 2, 3, 4, 5. I have to give this one like a polynomial because it's a trend. Okay, can talk about that in detail later on. And for the same thing, you can talk about summary and end. And let's see that this one that this the one that if I go back to that previous one, if you want to do the contrast, okay, GLM2 contrasting with respect to see contrast 2 versus the rest, 3 versus the rest, same thing. Okay, all these for the first one. Okay, if I do that for one more time. So you can see the result. We're gonna interpret the results in a large scale later on. Okay. That's example in a certain example. See. Syntax for single group trend analysis. See. Y1, Y2, Y3, Y4, Y5. But here we have like a see 1 person, second, third, fourth, fifth, sixth, 7, 8, 9, 10, 16. See. Again, see multivariate repeated measure results. We should know how to explain that one. We're going to do that one in broad, elaborately, very elaborately. Okay. So I'm just showing you for time being. And we are see contrast variable. Days 1, day 2, 3, 4. And big polynomial contrast. Polynomial. Why is a polynomial? It's going to be like a trend, would be like a linear, or that any polynomial type, because it has been taken over time. Okay. They are trend. Okay. We're going to talk about that one. For what I'm going to do that for time being, I'm going to give a rough idea for you to move forward, and then later on come back, and then we're going to do in a large scale. Okay, explain everything. So let's get back to this one. See. Okay. Okay, let's say that what's the third method, third format in the repeated measures. Look at the third one. Third one. Let's go to third one. Third one, I'm gonna say one between. See, one between and one within. It's called like that. One within, one between. Repeated measures. See, repeated measures design, no measures. Okay. Measures design. Okay. So repeated measures design, R&D. This one. Oh, sometime they're gonna call this one split plot design. It's another name for this one. Split plot. Let's say what kind of a situation. What do you mean by one between and two? One between and one within. One between and one within. I'm not talking about the group, okay? Be careful. The groups are gone. See the group. See, it's a group. One way repeated measures. One group. I'm sorry. One way or one group. Okay. The same way I can say that one. It's the same thing. Single group repeated measure design. Single group. I'm telling group to the individual. This is my group. See, this is my group. Group. See, it's the group. These are individuals. Again, over certain treatment or for certain treatment or over time. Same thing. See, one way, or that you can say that single group repeated measures. Okay, again within the subject's variable being that time. Okay, but here I don't see the group. I see that in between. One between, in between, and within. There are two things they can. I'm gonna write that example for you to see clearly that in that you get a clear idea. Okay. So what I'm gonna do, I'm gonna say here mainly the variable. Main variable would be what is the time. Repeated measures. It may be anything. Repeated measures factor. So this is the within variable. See, within variable. In previous example, within variable time. The first one within variable is what? The drug. This time. This has been measured. See, 2 months. See, 2 months. After 2 months. After 4 months. See, 4 months. After 6 months. Look at 6 months. So let's say that they were checking something like a weight loss. See, WGT, weight loss 1. Okay. WGT, loss 2. So they're gonna see that certain diet or the diet and exercise or certain how that certain they have proposed. I think this example. I think they have see that how that one of these method of that losing the weight gonna affect that one. Which method would be like they can compare and contrast at the end of the day. That's what they are trying to do. In the previous one, that see this one, what you're gonna compare in the very beginning, this one, what are you gonna compare in the first one? See, single group one, you're gonna study the effect of the 4 drugs. See? This here. So here the same thing that you can taken into that how that response factor would be that how that can be that compared and contrast among these 4 groups. See, for 5 days, within 5 days you can do that kind of a comparison. Okay, so here see the roughly. Okay, I'm gonna get into detail later on because I wanna just to build up this discussion first. So here they are saying that okay, within a like a one within, see, within variable is one variable. That would be the time factor. They're gonna check that their weight after 2 months, 4 months, after 6 months, after being that they've been treated with a certain certain method. Okay, so what are those are called the one between variable. That between variable we're gonna call the class or group. You can say the group, you can say the class. Then see between group, between variable. What is the between variable in this scenario? The diet. Okay, the diet. Diet. Between variable with diet. So they're gonna have a 3 levels for that one. Either diet and the diet and exercises. And in addition to that one, they have a control group as well. They're not gonna do anything. You have one group, one within variable and one between variable. One between variable would be the diet. Diet has like a 3 levels. Diet, only diet, and diet plus exercise. Which one's gonna affect to that the weight loss? And they are suggesting different method to lose the weight. If a certain person comes, look at that. If a person comes that he's that this one, forget about this one. Syntax multivariate match one. One between and one within repeated measures analysis. Is this the diet? That's the diet type. Either first type, first group, second group, or third group. See, you have a 3 groups. Each group, we have a weight loss. 1, weight loss 2. After first month, second month, third month. How many people been involved? How many people in each group? 1, 2, 3, 4, 5, 6, 7, 10, 11, 12. See, 12 people. 12 people. Same persons that the weight loss being measured after 2 months, 4 months, and 6 months. In that way, that's the way that if you really want to see that how it's going to affect us after a certain period of time for that one, you definitely have to design this experiment in a repeated measures manner to get this done. That's the key part over here. See? So you're going to measure their weight loss for the given person for the first treatment. See, it's the first treatment, the second treatment, and the third treatment is a control group. See? This is how the data will be set, taken, see? Then we're going to write this one. See, so here that in this case we have a so each one over here for the diet, let's say that we have a 12 people. See, for a given first one, 12%. That 12 people are going to have here 12, 12, 12, and the diet to 12, 12, 12, 12, 12, 12. See, right there. See? So this one being, see, this one for being, see, 1 to 12 individuals. This one 1 to 12. This one 1 to 12 individuals. But the same thing, see, that's the same thing for this level. See, same thing, same thing, same thing, same thing. So in between you have the individuals. They are readings. See? So here that if you get this one, you're gonna say that data. You can say weight and input. You have to give the diet. That means this time you have to include your what? You are definitely that in between variable. In between variable is nothing but diet. Any name that you wish to give, that one you can give variable diet. Okay, and then the other one is weight loss. WGT plus 1, WGT plus 2, and WGT. I can say this one WGT loss 3 after 6 months. Okay, WGT loss 3, and then you get the lines. And this one, see, 1, 2, 3, 4, see, 4, and then dot, 1, 2, 3, 4. This is for the 36th line. This is the first line. See? No. Each one has like a 12. I think 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12. Yeah. Then you, as usual, you're gonna go to the procedure GLM, and this time you have to give you the class or the group or the between variables. See, class is nothing but diet, whatever the name you have given. See, the model. If you want, you can put the y1, y2, y3. We use that WGT last one any way you want. You can define that one any way you want. Okay. Whatever you have utilized in the beginning should be utilized even within your model. That's it. That's all you're going to do. See, WGT loss 1, WGT loss 2, WGT loss 3 equals, this time you have something, see, diet. And no univariate analysis. They say don't, if they know univariate repeated measures. Okay, that's what it means. And the repeated one, which one is repeated? You have a repeated time. Time has been repeated. How many levels? 3 levels. And you can get the summary and means and end. See? Pretty much is very straightforward. It's not hard. Okay? We have to figure out for the given scenario how this can be get it done. But once we going through this all the ways of doing this one. Okay. So quickly, I'm going to go to the next one and then I can also stop. Okay. Then we can continue same discussion on Wednesday and keep going. Okay. So see, if you want this one, see, same thing. You get the results again. See, this one very important. We will talk about this one large scale and then how to make the hypotheses, conclusions, and everything. We're going to talk about that one. Okay. So let's go to the pretty much the other one. The other one is what? The fourth one. See, one between, this time one between. You have one variable in between one variable and two. See, two within for a given certain. See, two within. Repeated measures design. See, RMD. Let's look at a certain given certain example. Okay, you will be given a certain drug. See, you're gonna give a drug. Drug has two layers. See, drug 1 and drug 2. Drug 2. You know for sure this is what? Within variable. Within variable. For a within means for a given individual, within the individual. Okay, for a given individual, that means that particular individual has to experience those two drugs or take those two drugs, experience those two treatments. Not only that, they have split this one again. How? By giving what? Doses. See? See this one, dose. So you have a dose, then you can say dose 1. Dose 1 may be Y1. Dose 2, Y2. Dose 3, Y3. That's why you have a 2 within. See? Within this one, you have a dose. See? So you have a Y1. See, 1 is Y1. 2 is Y3. 3 is Y4. See? Then here, see, you have a 2 within, but you have only one between variable or group or class. It's nothing but there might be 2 groups, maybe placebo group and a treatment group, or control group and treatment group, like that. Let's say I'm going to call that from group 1 and group 2.
Can I ask a question quickly?
Yeah, sure. Go ahead, David.
Okay, with drug 2 under dose.
Yeah.
So drug 1, you have dose, you have 1 Y1, 2 Y2, and 3 Y3. Your 2, you have dose is 1 Y1, and 2 Y3, and 3 Y4.
No. 3. I'm sorry. By accident.
Okay.
By accident. Thanks for correcting.
Okay. I was very confused there because then 2 is Y3, so 2 should be Y2.
Yeah. Okay. Hold on. I'm gonna fix this one. Okay. 2.
Okay.
When I was writing, I was thinking something I think by accident. Okay, Y2.
Okay.
You're right.
Good.
Thanks for pointing this out. Yeah.
Good. I didn't want to be
1, 2, 3.
confused.
1, 2, 3. Sorry.
Good. Yes, that makes sense.
Yeah. Now, like a group 2 male and female. Oh, that 2 ethnic groups. They different things we can take into account. And then for the Y variable would be nothing but the reaction time. See, reaction time again. That would be measured for that group 1 and group 2. But the people in the group 1, they're gonna face into any individual in group 1 has to get how many times he has to do this one. He has to take the drug 1, 3 doses, and drug 2, 3 doses, altogether 6 readings for that one. Okay. So these experiments very heavy. That's why before the individuals gonna get into this one, we're gonna get their all that with their own discretion and then with their own willingness, they're gonna be participant because of some for different reasons. But anyhow, I'm not gonna go to their legality or their other aspects. I'm just focused, narrow down our discussion only to the theoretical aspect that involved with that one. But he has to take 6. 3 doses from this drug and 3 doses from this one, and each and every individual. See? So for such a case, how could we gonna set this up? Let's say that for data, I'm gonna write this one as code over here. Data something less or something. That's what they have given that, and I'm gonna use the same any name. Okay, it doesn't matter. Input. How do you put the input? You need the GP. I'm going to call the group GP, okay? GP for the group. That's the same name going to go to over there. And this one called the Y1, dose 1, dose 2, dose 3. Okay. Oh, yeah. I think this one, okay, we were right up to a certain point because I'm going to call this one instead of calling 1 and 2. I'm going to, because these are different. 4, I'm sorry. These are dose 1, but I would prefer to call that one dose Y4, okay? Y5, because it's a different reading, okay? Y5. I'm gonna do like that. This one Y6.
Because you could call it drug 2 dose.
Yeah,
Y1, 2,
some
3,
notation, any notation, whatever you like, but okay.
But the 4, 5, 6 makes it unique.
Yeah, that's what. Yeah, okay. Rather than call the 1, 2, 3 again, I can call that one, as you said. I can call 1, 1, 1, 2, 1, 3, and then you can call 2, 1, 2, 2, 2, 3, like that. Either way, it doesn't matter for my convenience. Okay. Anyway, so you can label it any way you want. So we have labeled under the dose 1, 1, 2, 3, Y1, Y2, Y3. Then under the drug 2, Y4, Y5, Y6 are 3 doses, same 3 doses. So I will call 4, 5, and 6. 4, 5, and 6. And then I go to the lines. Okay. You know that when you have that any individual have 1, 2, 3, 4, 5, 6. It based on how many individuals. See? 1, 2, 3, 4, 5, 6, like that. Okay. And then GLM, general linear model. And the model would be what this time? Model would be Y1, Y2, Y3, Y4, Y5, Y6, GP. See? Group, no uni. Okay. And repeated would be, you're gonna repeat it repeated under the repeated measure. What would be the your this one variable between variable within variable? Sorry, drug. How many layers it has? 2. Then how many doses we have? Dose. I'm sorry. Dose D. 3 doses. See? And run. And run. You see that we have an example for that. One between, 2 within. Yeah, see, one first in, see, first group, people in first group. These are the ones in the second group. But any individual that in this first group, how many? 1, 2, 3, 4, 5, 6, 7, 8. 8 individuals. Okay, 8 individuals. So here then this is the group, and then we are reading 1, 2, 3, 4, 5, 6, and then see. The same thing, and later on we have to interpret the given results. That's all we have to do. And but anyhow, to complete this one, I'm gonna finish that the last one too, in that way that I think last one, and then yeah, those two, and then show you that it's easy. Okay, and I can tell that the class will be great. That's okay. Real quick, I'm gonna show this one. The other one, 2 between. Now we have a 2 between variables and 1 within. Now 1 within repeated measures design. Okay, we can think about an example. 2 between, see, 2 between, see, but you have only one. Same example in the weight loss example. We can go to the classes. There are 2 groups. See, class for the group. See, for group, I'm gonna call that one GP. GP has what? And I'm sorry, the group. This one, there are between 2. One is what? One is the diet. The other one is the age group. Now, see, age group. See, your group would be, if you want, you can call GP. That's okay. This one, age. See, you have a 20 to 30 years and 30 to 40. See, now you have a 2 groups. Not the levels. I'm talking about the groups. Diet and age will be, those are variables. Those 2 variables, class and group variables. I'm gonna call the variables. For the first group, you can say the control group if you want a control group. Second one, you can call the behavioral model. Some model according to that only, exercise only, whatever that, sorry, the diet only. And this one, behavioral model mod class. Okay, exercise, something like that. Age group again, 20 to 30. This one, 30 to 40. 20 to 30. 30 to 40. See? So we don't have to be so much specific. Nobody gonna be like a 30 years. 30, which 30 gonna go to which group? Like a first one or the second one, doesn't matter. That 30 years and then certain months, if that's the case, you can go to second. Or that it's not a big deal, okay? But you can put into any group if somebody's on 30 years old, okay? But then here you have a what again? Within variable, you have only one. See, let's call this one time. This one, this is a within variable. See, within one time. Then you're gonna check that one again, but see, after 2 months, see, 2 months, see, WGT loss, see, 1, see, loss 1, this one, see, 4 months, WGT loss, see, 2, and this one, 6 months, see, WGT loss 3, we can call that one, see, like that. So for this one, if you go ahead and do this one, see, data, you can see the weight, see, weight 2, input, see, you have a diet, you have an age, you have a Y1, Y2, and Y3, see, you can call them Y1, see, Y1, Y2, and Y3, see, the readings, and the lines, see, and again, same thing, see, of GLN, and the class would be what? Class, there are 2 classes, one is diet, this other one is age. Then the model would be Y1, Y2, Y3 equals to diet and age both, okay, see? And repeated one, repeated measure would be what? The time. That's the 3 layers and run, okay? That will give you that whatever the results that we really need to have, that one. And the last one would be 2 within and 2, okay? So this one I'm not gonna write the SAS one, the last one 2 between and 2 within, okay? 2 within and okay, 2 within and 2 between, 2 within and 2 between. Repeated measures design. Think about that. There are, see, you have a grade 4, you have a grade 6. Okay, they're gonna look in the IQ. Sometimes they have a high IQ, low IQ in the student. See, high IQ, low IQ. See, at the same time, that experiment has been done in 2 ways. See, 2 forms. FD form. Okay, I'm gonna explain this one. Okay, for time being, just and the time after 1 and 2, 1 and 2 maybe after 1 month, 2 months, or that after, see, here 2, see, here 2, and here 2. Like that. See, some kind of experiment like that. But I can talk about that one in a detail that next time, and then get into that one, and then we can broaden this discussion and then talk about the multivariate, univariate aspect, and then the epsilon, especially that we have to talk about that one. And then I don't think that's all we have to do mainly at this primary stage. Okay, what I'm gonna do, I'm gonna stop over here. That let's meet on Wednesday. Okay, Wednesday, that while we're going through the homework too, that we can add more discussion on this one, and Thursday too, we have plenty of time to finish this off. Okay, so if you guys don't have any questions, anything, I'm gonna let you go. You guys have a good night, and then see you on Wednesday. Stay safe and be well. Okay, take care.
Good night, Smith.
Thank you. Good night. Thank you very much. Thank you.
Good evening.
Good evening. Thank you. Take care. Good night.